All right, so let's start our session with the some examples from the worksheet that I shared with you also. So let's open this one. I didn't have the worksheet. Okay, just do this one. Open this up. All right, so this is the worksheet. Let's do some of the problem. Give you some idea of the this problem. Okay. All right, so the last problem. Right. So this is the problems. So think about a helix and see a particle moving along the helix. Helix is in one direction, it is a circle, but in z directions, one of the direction, it is moving up or moving down, or can be something in between. Okay, so you see that the I and j components, it looks like a circle, so sine and cosine. Okay, but the k component is a polynomial. Okay, so this is a helix. Helix meaning something that looks like this one. Let's start from sine. Sine must be so 0 here. Something that looks like this one. Okay, so that's a helix. All right, so let's see here. Okay, so R is positions. Okay, so this is the positions. T I cosine t k plus t square minus 3t plus 2k. Okay, so if you see these directions, z is moving towards us or away from us. Okay, so moving towards or away. And y is moving left and right. Okay, in this according to this position of the axis, and z is up and down. Okay, so towards or away, y is left and right, z is up and down. Okay. So question A. Question A is about find the time when the particle is moving downward. So moving downward meaning in z directions. Okay, z directions. That is, so I'll say this is x of t, this is y of t, this is z of t. So problem A meaning that the the speed, okay, the velocity, up down velocity is negative, moving downward. So this meaning up down velocity is negative, right? So up and down velocity is the z. So in this case, up down velocity is z prime. Okay, so that is 2t minus 3. Okay, and we want to have something that's negative. So meaning t must be less than 3 half. Okay, say from t positive. So this is up and down, going down. You check the sign chart. Okay, so starting from 0, this is 3 halves. This is going to be negative here, going to positive there. Okay, so using this sign, you have this is going downward. This is going upward. Okay, so that's basically questions. Find the time when the particle is moving down. So the particle is moving down. For t between 0 to 3 half. Okay. And part B, does the particle ever stop moving? Well, that is the question about when moving means all the components are 0 at the same time. Moving meaning that the uh, all the speed, all directions stop moving meaning at the same time, 0 at the same time. Okay, so let's check here. So x prime, let's see, x is sine, so it becomes cosine. And y prime is sine t. Okay, sine and cosine t. So here's the z prime 0, that is 3 halves. Okay, okay. So sine and cosine are the same. Just checking here. All right. So see, this is sine, this is cosine. So it's twice here. Okay, so here's in pi over 4. This is, let's see, what is this? 5 pi over 4. Okay, so, but none of these are same as this one, 3 halves. So, so question is there any t so that x prime simultaneously? So apparently no, because Here from x and x prime y prime can be 0 at, sorry, they are the same at this point. So at different points, they are distinct. Okay? So no, not possible. See, if cosine 0, then sine cannot be 0. Okay. All right. So the question is sine cosine t cannot be same. Uh, I think that's enough explanations for this. There are no t's making x prime, y prime, z prime 0 simultaneously. Okay. So let's see. See if does the particle ever reach the height 12 unit above the ground? Okay. So let's see. This is 12 unit above the ground. So this is talking about the z direction. So k directions. So we're solving z equals 12. The z of t equals 12. Okay. So because z is now, what is that? 3 square t square 3t plus 2 equals 12. We'll check whether we can solve this one. So we're solving this minus 10. All right. But we still can do factorizations here. So this is t minus 5, t plus 2, I guess. Yeah. Okay, so t equals negative 2 and 5. But because from the beginning, it asks for positive, non-negative t, so we dismiss this one. Okay, so it's reaches the height 12 at t equals 50. Sorry, t equals 5. Okay, and part D, find the velocity and speed of the particle whenever it is 12 units above the ground. So at this time. So here, uh, velocity. This is velocity vector. And the speed, this is speed. Okay. Velocity and speed. Okay. This is velocity. This is speed. Okay, so that's easy. So it's sine become cosine. 5 radian. So this is I. And then cosine becomes negative sine. J plus 2. Sorry, we take derivative. So 2t minus 2t minus 3. So 5 that's 7. 7k. So that's the velocity. And the speed. Velocity a factor. Speed is a scalar. Okay, so cosine square 5 plus this is sine square 5, that's 1, plus 49. So this is 7 square, take square root. Okay, so this is 49, this is 1, so this is square root of 50, so 25. So that's the speed, unit speed. Okay. Questions? Questions?
Yes, sir.
Yes. Uh-huh. All right. Okay, so that's about the this chapter. Okay, and now we continue with this with the uh, what's called surface on free space. In free space. Show you um, this is generic surface. So in general, this is what we call quadratic surface. What is a quadratic surface? Quadratic surface is say uh, a polynomial in terms of uh, x, y, z here. So in let's see in three space. All right, so let's see, for example, this one, before I continue, it's just in illustrations. We'll do some illustrations later using Wolfram or Maple. Okay. So for example, I'm going to draw something like y squared plus z squared equals 1. Okay, so what's the graph of this one? Okay, and how to do this one here? Okay, so what we are going to do is making some cuts. How to get the picture of this? So make cuts. Um, cut away from three directions. Three direction is x, y, z. Okay, so x constant, y constants, and z constants. Okay, so let's see here. What about if z constant? Z constant. Okay. In this case, z cannot be bigger than 1. Okay. Here, z must be -1, the smallest, and the largest would be 1. If z equals 1, then x and y should be 0. Okay. Same thing. If z negative 1, so it only happened when xy equals 0. So when z equals plus minus 1, then should be 0. Okay. So that means if you make a cut here, say this one, this is z equals 1, then you only get this point. Okay. All right. What about z equals 0? Just substitute z equals 0, then you have plus 1. Z equals 0 is this plane, xy plane. Okay. So that's circle, radius 1. Set circle. All right. For example, what if c equals 1/2? Say 1/4, plus or minus 1/4. So just take whatever. Yeah, 1/4. Then if you plug in 1/4, you get x plus y squared equals 1 minus this is 1/16. So okay, so here you get 1/4 of this one. You get slightly smaller. Okay, also here. And what about if say z equals 1/2? Z equals 1/2, then you have this is a 1/4, so 3/4 there. Okay, so you get this one. All right. So in the end, if you make a lot of cuts here, then you can reconstruct what kind of object is this. Okay. So this one is turned out to be a sphere. Okay. Okay. So CT scan or MRI works this way. It cannot it reconstructed the 3D shapes by doing these cuts. Okay. So this is how to get uh, a surface. Sorry, yeah, surface sphere. All right, another. Let's see, because this is sum of squares, right? Then that cannot be negative. Okay, so meaning the the graph or the object should be above the xy plane. So let's see. If you make a cut on the z constant, z cut. All right, so when z equals 0, you get, okay, so only you get this point if you solve those. Z equals 1, then you get a circle of radius 1. Say this is 4. So this is 4 equals 2 squared. So a circle of radius 2. And for C equals K. Okay. So this gives you circle of radius K. You only have, then you have a circle. Then there you go. Okay. And so you may wonder how we should do this one here. So this is the cuts, right? And YZ. Let's make the cuts in other directions. Okay. In other direction, for example, when x equals 0, uh, other directions. So x equals 0. When x equals 0, you get y squared equals, uh, sorry, what should be z equals y squared. Okay, so this is a parabola. Okay, so this gives you a there. Okay, and it turns out to be something that we call a paraboloid. Okay, with vertex paraboloid. Oh, with vertex opens up, vertex here 0. Okay, and okay, and then one more thing is about z, and we'll do the other on maple. Okay, so z equals, say this one. Oh yeah. Okay, so this is, so when same strategy, find the cuts. Okay, so with some cuts, z equals 0, for example. When z equals 0, you have x equal y squared. If you solve that, that means uh, okay, so you get this thing. There. So y equals x and y equals negative x. Okay. When z equals 1, z equals 1, so the height 1 is the, 1 is x squared minus y squared. Okay, so again, but recall that this is hyperbola. Okay, so hyperbola with a something that looks like this one. Yeah. If x cannot be zero, right? So this is hyperbola. Okay. And you make another cut, for example, z equals 2, you get 2 equals x squared minus y squared. That's another hyperbola. Okay, so how you should this hyperbola looks like. So what's the shape of this? This is what we call a hyperboloids. So let's do on maple something that looks like this one. Say z equals a x squared plus b y squared plus 2 plus x plus e y plus f. So a, b, c, f are constant. Okay. So let's do some. Uh, let's plot this one maple. In can you hear my voice? I get a notification. Speaker is not working properly. Oh, speaker, not the mic. All right. So okay. All right. So let's do this one. Just do working. Okay. So let's see. Let's uh, plot the one that we had earlier. X squared plus y squared. Z equals this. Uh, okay. When x equals say say -2 2 y is the same. Okay. sorry, get this command. Plot 3D. All right, so this is the thing. This is parabola. Sorry, paraboloid. Okay. Why this? I should be able to move this one. How to take this is a parabola. Should be able to move this one out. So let's make it bigger. All right. So let's. All right. So this is the graph. Okay. So you see from the top. So you see XY plane. This is XY plane. And what you mean by making the Z cuts is doing this way here. So you see the cuts are circles. Circles. Okay. So this is a paraboloid. Paraboloids. Okay. Let's see what's what to be. So instead of just x squared plus y squared, you put a square root. So square root of x squared plus y squared. So let's see what's the difference. So x from -5 to 5 and y from -5 to 5. So, oh, sorry, this should be. Oh, this is rather sensitive to errors. Uh, this should be here. Yeah. And redundant here. Okay. So you get a cone. Okay, get a cone. And let's see what we have if the thing that we try to plot. Last one is z equals x squared minus y squared. X, say -5 to 5. -5 to 5. So something that looks like a horse saddle. In fact, we will call this a saddle. And this point here called a saddle node. This is part of the what you call paraboloids. Sorry, hyperboloids. So hyperboloids. This is a called paraboloids, and it is a cone. Okay, and what else? And this is 3D. Okay, now let's see. I want to plot a sphere now. X squared plus y squared plus d squared. A equals 1. Okay, so x from not to y from negative to 2, z from a to x, so just symmetric all the way through. What's wrong with this one? Oh, here, you see, this is not equal sign. Okay, okay, so something that looks like this one. Let's make it bigger. Say 3/2. So this is a sphere. Okay. And let's see if we implicit plot and then we put 2 here. What about this one? It just becomes what they call an ellipsoid. Okay. What about if I change this one to negative? Oh, so it looks like this one. Okay. And what about this one? There's 2 negatives. If you put 2 negative, well, 2 separate things. What about if just put this one? Yeah, maybe I should get x more than this one. X equals 4, for example. Not good. 1 to 1. This is negative 1 to 1. There. Almost just like two sheets of paper, just part of this. Okay, so this is how you should use the, if you have a Maple or Mathematica, have Wolfram, you can use also the, if you have the Android, you can use this to do some plotting. Okay, so this is a good starting point to use the apps. Okay, and there are, let's say, 4 generic things you should be able to recognize is a ellipsoid. Okay, which one? Oh, we have that already. Ellipsoid, paraboloids, cones. This is hyperboloids. And this is also hyperboloids. Okay, but you have separate things here. Okay. All right. Okay. Questions? Let's do this. Oh, alpha or well, Wolfram is Mathematica actually. Whatever you can use your apps is. All right. And I hope that you can just play around with the apps and to plot many things in 3D. Say what 3D this is the equals say sine x plus sine y. So x equals say minus uh, say 7 to 7 y from minus 7 to 7. So this is like the shape here. All right, so this is the cartoon. You have a board storing eggs. For example, this is the shape. Okay. And you can make combination of this. For example, why not multiplying? All right, so let's just multiply. And you get similar shapes. Right? We see a lot of ragged things, peaks and pits. Okay. Or you can try these combinations. This is sine. What about the other is cosine? Well, you get the same thing basically. Okay. Or you get plot 3D at the so this is the exponential of say minus x squared. All right. Oh, I put this minus plus y squared. What kind of case do you have here? Say from x from -1 to 1, y equals to -1 to 1. Well, if you pick something bigger, you can see the shapes, right? It looks like a peak. Maybe that's too big, and you can do experiment of this. So just say 3. Not necessarily same here, so just up to you. All right, so just a peak. And outside the peak, it's almost a plane. Okay. Why plane? Well, this is exponential is negative, negative exponent. So this must be small. Okay, so it's almost 0 here, almost 0 here. Just one peak. Okay. So there are a lot of things you can do with this plotting. All right, so that's something that I would like to show using Maple Wolfram, and we would like to use this more often later on to show you the plot, to give you an idea about the 3D shapes. Okay, so the generic thing is uh, the thing that you should be able to recognize is ellipsoids, paraboloids, hyperbones. Right, so those are the stuff that I would like you to be able to recognize. Okay. All right, so we'll stop here and take a break for 5 to 10 minutes. Okay. So let's stop the record.